screen, I will show like I will just revise on the slides, and then here it will be the screen of the code. I have like the code ready already, but it's better to write it like step by step. So I have already prepared the codes. I will like looking to this screen, copy the code to here. But we will not copy, we'll write it together. So like you have like more emphasis on what we are doing. So let's start with our slides. This is our table of content. Uh, Introduction, what is CUDA, why is CUDA, what is the grids, blocks and threads, host and device, writing CUDA program. So like we just like we'll refresh our memory with those slides. Uh, I believe like we have covered all of this, but I believe like have forgot most of it. So like let's just refresh uh, what we talked about last time. So first, if you are writing code, if you are doing anything on your laptop, everything will bypass your processor. But the problem is that the processor is like, we can say it's efficient, it's very powerful for sure, and most of the tasks is done on the processor. However, the processor have like maybe one drawback is that it is limited by the number of cores. So like your processor can be like 6 cores, 8 cores, which means that you can do 8 processes parallel to each other at the same time. So you will be limited to the number of cores you have. For sure, like each process like take few microseconds, so the processor is very, very powerful and very efficient, that you will not notice how much time you have spent, or you will not notice that there is a lag between the tasks. It can do like really million of tasks in just a second. So it's very fast. However, it's still a limitation if you are doing like a heavy mathematical problems or any kind of stuff like this. So that's where we come to like parallel programming. So let's give like example for this. So imagine that you have a Coke machine, and the Coke machine represent, for example, a processor. So if you have like one Coke machine and you have like 2 queues, so for example, like each process take, for example, 1 second. So for the 2 queues, you will take about 20 seconds. But if you have two Coke machine and the same 2 queues, so like if each one like go for if each queue like go for a machine which is a core here, so it will be only 10 seconds. That's the same idea of the number of cores and what we are doing here. So the more number of cores we have, like the less time we'll spend like doing a process. So here's like a quick comparison between the CPU and the GPU. So for example, like as we said before, like the CPU or Intel CPU, which is i7 or i9 or AMD Ryzen, it's limited by number of cores. So like your processor can have like 4, 8 cores, like it's limited by number of cores. But your GPU can have like thousands of cores. It can reach like, for example, 6,000. So here's like this is like a main difference between them. So like the GPU can do more processes in parallel. However, the GPU can be maybe like slower than the CPU, but at least it can do it in parallel. So like we'll gain we'll gain time for sure from that. What else? So like this is like a general idea on the difference between the CPU and the GPU. So as you can see here, like the CPU is limited by number of cores, but here's the GPU like have thousands of cores. So we know that like three companies in the world that produce GPUs. There is Intel, and there is AMD and NVIDIA. For sure, NVIDIA is like the most popular and most powerful between among all of this. Nvidia company now have it's like about $2 trillion. Yeah, $2 trillion of net worth. So like it's really big company. What make Nvidia like more popular than the others is that uh, they are not using their GPUs only in like gaming or graphics or like it's not used by the operating system only. It is allowing like programmers and scientists to use their GPU. She is like NVIDIA is giving like a programming language called CUDA that scientists and developers, gamers, anyone can use it to write like a specific code that do like a specific job on the NVIDIA GPU, and this like give you like a very performant um, like a very performant like tasks. You can like do your tasks in like no time, less time for sure. So this is like developing the AI significantly. That's why like we are using like NVIDIA for that. So what is CUDA? CUDA. CUDA stands for Compute Unified Device Architecture. As we said, like CUDA is a platform and the programming model for CUDA-enabled GPUs. So like with CUDA, you can only write programming or a code for only GPUs that is produced by NVIDIA only. You can't write with for like AMD Ryzen or you can't try and write for Intel. It's only for NVIDIA because like it's produced by NVIDIA. As we said, the platform exposes GPU for general purposes computing, so anyone can use it. You can use it as an AI engineer. You can use it as a game developer. You can use it as anyone. So like NVIDIA like allowing you like to use their GPUs for your specified task. In CUDA programming, both CPUs and GPUs are used for computing, and we'll know like what is meant by CPU and GPUs are used for computing. Uh, CUDA is written with C language with minor differences and different compilers. So if you are a programmer that knows how to write C, then it's your lucky day. Actually, the CUDA is similar to the C language. You will find like a lot of similarities, and it will be easier for you to write CUDA if you know C. Also, like we can say that there is APIs that allow you to use CUDA for Python and for other software as well. Our focus will be on the C CUDA. It's like maybe the main language for CUDA. So we'll look into this more. So why CUDA? CUDA, as we said before, can achieve high parallelism and efficiency than general purpose CPU. It can give you like better performance. If a task that can take a millisecond, you can do it in 10 seconds with CUDA, and this like enhances speed significantly. So grids, blocks, and threads. What is the grids, blocks, and threads? It's like we can say it's like units in the CUDA memory. Like we can say that the grids contains blocks and blocks contains threads. So the threads here is the course that we talked about. Each thread can do like one process. So we'll explain this more. So here we have like uh, the grid. Each grid is having a block and each block having a thread. So this is a block with a thread block, and this is a thread. Each thread can do like we can represent it as a core, and each like core is like have like maybe each we can talk about block. Each block have about like 1024 core, and we have like thousands of blocks, and we'll talk about this later. So here is like a grid. So like we can have like a grid, as we can see, and each grid can have a block, and each block have like multiple threads. So like it's just like a hierarchy of in the memory of the CUDA itself. So let's talk about host and device. What is host and what is device? So like in host is another name for CPU, and device is GPU. So like when we are saying like we are copying from host to device, it means that we are copying data from the CPU to the GPU. If we are saying we are copying from device to host, we are returning the result from the GPU to the CPU. So like this is the default steps on what we are doing with CUDA. So step one is copy data from host, the CPU, to the device, the GPU. Step two is doing the computation on the GPU itself. The last step is that we copy the result from the GPU to the CPU. You can't uh, we can say like you can't use the data while it's on the GPU. You need to have it from the GPU to the CPU, because like as we said before, like the CPU is handling everything, everything that is coming on your screen, anything that you see, you click the mouse, anything. It's need to be handled by the CPU. It's need to pass by the CPU because before it comes as an output on your screen. So like that's why we need the CPU at the end. Anything you do in order to like be shown for you or you use it, it needs to pass by the CPU first. So lastly, writing the CUDA program. Here we will like dive more into this, but like maybe we need to emphasize something. So uh, if you are writing C program, then you have like the headers and then your functions and the main. The main is the main block that can call your function and execute it here. In a CUDA program, we have almost the same. We have like a function and the main body, which can execute the CUDA function. But the CUDA function is called kernel. So like you will hear this a lot. You will hear like kernel, uh, call the kernel and this stuff. So like it's the same as a function in normal code that's run on the CPU, but in CUDA we call it kernel. Uh, and actually, the calling of the kernel is a little bit different from calling the function. So, like for example, here is a void function that doesn't take anything and return nothing, just like delay anything. We just like call the name. We just define the function here and call the name here and the brackets, and then it's executed. But here in the CUDA, as we can see, there is like a three braces, and we write one and three inside places, and then like it's the same actually as here, but just with this three braces and the numbers inside. So what does this means? It means that here it's one and one. The first one is the block. What is the number of blocks we want to use? How many blocks we want to use for this kernel to be executed? The second one is the number of thread per block. How many thread or how many core per block we want to use. So like they emphasize these parts and they are important. So for example, if imagine that you have uh, an array of 10,000, and then you choose your number of blocks to be two, and you choose your number of threads to per block to be four. That's not enough. You will have like two blocks, each one have four threads. So like two by four is eight, only eight. You have eight, while your array is 10,000. So like this is not enough. You should ensure that the number of cores, the total number of cores you are using exceeds the number of array or the number of process you will be doing on the GPU. and we'll talk about this more. Last thing is the CUDA device synchronize. This is a very important function, and I will show you like why it's important. However, like what we want to say here is the CUDA device synchronize is just ensures that nothing in on the CPU will be executed before all the processes on the GPU is executed. So, and we'll see like how it can affect our program if we don't use it. In some cases, we need to use it. So let's start with uh, our code. So like here, I was testing something. So, so let's start our hello world program. So I will make a new file. Hello CUDA.cu. So the extension of any CUDA program is .cu at the end. So just a moment. Okay. So let's write program together. So first thing is just I will include the required library. I will include like the standard IO stream library. This is only for using the print function because I can't use the print function without this library. So we have, as we said before, we have two important blocks. The first block is the kernel, CUDA kernel. The second is the main function. So let's start with the main function. So it will be, so always start with integer. If anyone like writing C, it's just like uh, very important. This part is very important. So like main, and then you open a bracket and you write at the end return 0. And your code should be written here. Your code. Here we will write like the CUDA kernel or the CUDA function. So uh, normally in C, we are writing like this. Void, for example, if I don't want to return anything, hello, CUDA. So here we just want to, but here like this is a normal C function. For a CUDA function, it's a little bit different. We should add like two double underscore, then we write global, then another two underscore, as you can see. Why we are doing this? This means that this function is not executed on the CPU. This function is executed on the GPU. It's a device function. That's why we are calling it kernel function or kernel. So unless you write this global, this code is will be executed on the CPU. So like this global tell like that your code that this function needs to be executed or run on the GPU. So let's just print hello from, as we said before, like when we call this function, so for example, we will call this function. So how we call it? Hello, CUDA. This is typically how we call a function in CPU. But here, this function is related to the GPU. So we need to open three braces like this. And we give a number and another number. And we close three braces again like this. So here's we are saying that this is a number of block. So let's, for example, give it as a number integer. Number blocks. Let's, for example, give it 3. And each block will have, let's here. Each thread, for example, will have like, uh, for example, let's just make it 4. So here I will give it the number of block. Here I will give it number of threads. So what we are saying that I need to use 3 blocks, and each block have 4 cores, 4 cores. So that means that I have like 3 by 4, which is 12 core in general. So this function should be executed 12 times. So let's just here, like, we will the NVCC is just like the GCC. It's a compiler that compile your code and transform it into machine codes that then you can call it and be executed. However, like, there's a compiler for the NVIDIA provide. It's depending on the GCC, but it have like some different stuff in it. So the compiler is called NVCC. It's from NVIDIA. So dash O, we will call our output program hello, and we will call our function, call our code. So if we call this hello, execute it. Ah, so can you see, like, when we executed, nothing, uh, like nothing appear here. Why? Because we forgot to add the CUDA device synchronize. The CUDA device synchronize is ensures that we will not end or the CPU will not continue before it have like all the GPU stuff. So like, for example, here, like, what we are doing is that the this function is executed on the GPU, but the CPU is not waiting for it. So what we need is that to see our output, we need to add the CUDA device synchronize. So here we are telling it, like, the CPU just wait until the GPU finish its task so we can see what is the GPU is doing. So let's build it again, and then let's call it. Okay, just a moment. It's just writing it beside each other. I forgot to add a new line for each one. Let's again, and as we can see here, we have like 3 blocks, and each block have 4 threads. So as we can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's correctly 12. So like, this function have been executed 12 times as we expect. But how we know, like, each one, which thread and which block have been executed it? So CUDA provide like something called block ID and thread ID. So here is an example. So let's look from block. Here. So here, block index dot x. As you can see, like, the I is the only capital letter here, and another one, thread x dot x. So what we are doing here is that we each block have like a number of threads. So like here, each time this function is executed, executed on like one of the cores that we are provide. So like we have like a three blocks. So block one, block two, and block three. And or we can like start from zero, block zero, block one, block two. And we have like each one have like four thread, thread zero, thread one, thread two, thread three. So each time this function is executed, it will tell us like which block is executing this kernel and which thread is executing this kernel. So let's build it and see. So as you can see now, hello from block number two, thread number zero. Hello from block number two, thread number one, and so on. As you can see, it's also 12 times, but it's specified for you like which block and which thread. And as you can see, it's not by order. It's, for example, executed two first, and then one, and then zero. So this is also a feature of CUDA. The CUDA is doing everything in parallel, so you can't expect like that all the process will be done in an order. You can expect like they are all done in this at the same time. So the output will come to you as soon as it finish and transferred. So like they can't be like in an order manner. It can be like just random. And every time I run this code, it give me like a different behavior. And for you, it will be the same. For sure, like when we like get more advanced in CUDA, we'll know more and more how to handle these cases, and if like maybe our program needs to be carefully in order, then there is some cases that we can use, but that's just for your knowledge. It's just not in an order manner. It's just give you whenever something finish and all of them are executed at the same time. So if you are giving it an array of 10, 100 million, then the last piece of the array can be done faster than the first piece of the array. It's just, or they can be done at the same time. So everything is done at the same time, probably. So that's a feature of CUDA. So this was a hello world example. Now we need to go for maybe more advanced example. So we will try to write a code for to see the performance between the CPU and GPU. We will try to write a code that just make an addition of two arrays of size maybe 100 million and see the difference in time between these two processes on the CPU and on the GPU. So I will to write it from scratch with you, but some functions I will just copy it so we save some time for questions. So let's write a new program, CPU, this GPU dot cu. So here we have like a new file. So I will just copy. This is the headers that I will need for this task. Chrono is just for calculating the time. CUDA runtime is just for getting me if there is some errors. The standard and standard libraries is just for printing purposes. So let's start. Here is we define. So this is like a function, you can find it everywhere. It's just this function that when you are doing some process for CUDA, you give it, because like, I will tell you where is the problem. Here is the problem that when you are writing a program, it's the errors that you get when you are writing a CUDA program is a runtime error. And the runtime error, you don't know where it is or what happened. Not like a normal error when you are writing on CPU, it give you like that you have a problem in line number, blah, blah. No, here it will not say this to you. So you need this like check error function to like tell you like what is kind of error you have. You have like an error in the transforming of data from the CPU to GPU, or you have function inside, or where it is. So it's just like it helps you, but you can just ignore it for now. We have an array, integer array of size 100 million. This is 100 million array. Uh, integer the block. We can say that this is threads per block. Let's for now choose it as 520. So we need, so like each block, it have like a size of 520. The maximum is, max is 1024. Can be more for sure, like it's depend on your GPU, but usually it's 1024. So we choose like it to be 512. So each block will have 512. However, like our array is 100 million. So we need to make sure that we have number of blocks multiplied by the thread per block is enough to cover this number and exceed even. So this is a very important part, and I will show you like how we can do this. We have here the kernel, what we call the kernel. This kernel will get two input arrays. And we will have the result in the third array. So like A and B are inputs, and C is the result. And it also will have the size of the array. This is like the size of array. So we should pass this at the last part here. And then the function. So this is like a CUDA function. Oh, sorry. So here we wrote like a constant, but we didn't specify the type. That's why it gave us an error. So here we should like write a float. So here is a constant. What is the difference? Why we wrote here constant and here we didn't wrote constant? Here we wrote a constant. You write a constant when this input you will not like you don't need like to mess with it. You don't need like to override the value in it. So it means that this is an input and this is an input, and I don't want to play in these values. But here we can't write a constant because we will write the summation between A and B in C. So we need like to override the values in C. So that's why we can't write a constant here. So that's the difference. So for the function, so integer index. So for example, like I have here like it's of a size 100 million or whatever, and here's also of a size 100 million. So we need that each thread in a block to have a one index, only one index. So like each core can access only a specified index. So how we write this? We write this in this way. You remember the thread index dot x plus block index dot x time block Mention dot x. So what is this? What we are trying to say here? What we are trying to say here is that, just let me get this. Let me get it to the other side. Okay, let's just give an example for this. Let's just imagine that we chose our number of blocks. Imagine that we have like the last example, that we have 3 blocks and we have 4 threads for each block. So what we are saying here that, for example, like I am in the first block, the 0 block. So this block index is 0. And I am in the thread number 2. This means that this index will be 2. So it just only point to the second element in the array. So imagine that I have, for example, imagine I am in the block 3. It means that this will be 3. Or imagine, yeah, I'm 3. So this will be 3. And the thread x number 2. So this will be 2. But what is the block index.x? It means that, for example, each this is the number of threads per block. So the number of threads per block, I can get it from here. So for example, I have like each block have like 4 elements, and I have 3 blocks, 3 main blocks, and each block have 4 elements. And I am in the third block. This means that in which thread I am. So it means that the first one have 4 and second one have 4, then this is 8, and I am at the second one in the third. This means that you will add 2, then you are in the 10. So it means that 3 multiplied by 4, or 2 multiplied by 4, because like we are starting from 0, then it will be 8. And you are at the second index, then 2, then you are at the 10th, you are pointing to the 10th element. This ensures that each core is pointing to a unique element, only unique element in this array. And that's why we are using this. This is like a variable that we are not declaring. It's just from the CUDA. So like each time you are accessing a specific core in the CUDA memory, you can just call this block index. It will say to you like this thread or this core in which block and in which thread. And will tell you also the dimension or the number of threads per block for that you specified before. So after specifying a unique index, we can just write, this is capital, for A index. Here is just the addition, B index. Okay, so that's it. But here we need to make sure from some things. So like it's not always that the number of blocks that you specify and threads per blocks can give you like the same number as you specified here. So like for example, you can have like 100 million, but here you can have 110 million block. So you can, or threads, sorry. The total number of threads exceed the number of the array size. So you need to make sure that if the index is greater than index is less than, for example, the DS, this means that you can do this. If it will enter only if you are in a block that is or on in like you are accessing a thread that is in the range of the size of the arrays that you are given. So if, for example, like I'm in a thread that is 100 million, 105 million, then I will not be able to access the array in this value because the array is already of a size 100 million only. Even if I'm in 100,000,001, I will not be able to access this. And that's like, maybe you can say it as a safe key for us. Safe key. Write it beside that. So here, like our function, we finished our function, our CUDA function. Let's write a similar function, but for the CPU. This function will be run on the GPU. For the CPU, we will write void. Let's just call this v add vector addition GPU. Just a name. And this is vector addition CPU. Here we don't need this global because this will run on the CPU. We'll have the same as here. So for here, it's just a normal for loop as we always do for integer I equals 0, I less than yes, I plus plus. E, I, 1, E, I plus E, I. So this is equivalent, exactly equivalent to this. They are doing the same, but here it's done on the CPU, here it's done on the GPU. So let's start writing our main function. Try to write it fast more so we can see the difference. I will just try to copy from my code. So let's just, we need like, we need to specify like our inputs, which is HA, for example, and HB. This is our input. So input arrays, input arrays on CPU. And we will do the same for the others. Let me just copy it. This is like the HC GPU and the HC CPU. This is the result arrays. And they lie on the CPU as well. Even like the HC GPU is lying on the CPU. But here, the DA, DB, and DC, they are a CUDA memory arrays and they are on the GPU. So here we are declaring that I have like a pointer of float of these objects. And if some of you like have a knowledge of C, this is like how we do it. But allocating a memory for these arrays is different for each one. So like if I'm opening for an array on the CPU, then I use the following. So here's I am saying that HA, HB, HC GPU, and HC CPU, I need you to open a memory in the CPU with the size of this size, and it's of a type float. The float is, as I remember, it's 2 bytes, 2 bits or 4 bits, I don't remember. So like it just will open you like this number, just like 100 million multiplied by 4. So it will open you like a size in the memory, on the CPU memory for this. But if we want to do this for the GPU, so like for the device A, device B, and device C, it's on the GPU. So what we need to do is the following. Let's just do one of them and copy the other. GPU, memory, and location. What we need to do, CUDA, malloc, and we give the reference to, for example, the device, the first one, and we give it the size. Do you remember the size that is 100 million? And we multiplied this 100 million by the size of load. Size of load. And then, so by this way, we are saying that I want this pointer, I want like you to open a memory in the GPU with 100 million size and the size of load. And the same for the DB and DC. And here we are just putting like the CUDA check error, just like to say like if we have like anything wrong here, it just will give us an error. Last thing uh, here, we need to give a random values. So here it just we don't do anything. Here we are just giving a random value to the HP, the input, the HP and the HCGPU. We are just giving it a random value. We are just filling it. Before like we are giving it to the function to make the addition. And last thing is to call the CPU function and the GPU function and calculate the time. So for to call the CPU function, what we need to do is that we add CPU and we just give it h score a, h underscore b, and we give it the h underscore c that it will write in it. As you can see here, yeah, here. Let's give me this. Oh, okay. And then we give it the size of the array. So that's how we call the CPU function. And to calculate the time for like the time for execution, we will just use this. We'll put this before it. And we will put this after it. And we'll just calculate the time. So this is only for calculating the time. We can. So let me do the same for the GPU. Quickly, I'm trying to be as quick as possible. So for the GPU before, do you remember like those steps that we talked about? Before we are calling the GPU function, we need to copy the data from the CPU to the GPU and then copy the data back from the GPU to the CPU. So let's do this. How we can copy the data? We need to copy the data from the, we are using this function, mem copy, not 2D, only copy. We want to copy the data to the device array from the host array. So we need to copy the data from the CPU to the GPU. That's how we do it. And then we specify the size. So it's this size multiply size of load. And then we CUDA mem copy host to device. Then we open it. So here we are transform the data from the CPU to the GPU array. And we will do the same for the other one. And just this one. Okay, so here everything in place. And how to call the function in the GPU, then we will add the GPU, and it will be the same as here, exactly the same. Can even like take this copy and make it like this. We just make this GPU. So this is the kernel function on the GPU. But the only difference is that we need to open these three brackets and close it. And these three brackets will have like this. And the first one is having the number of locks, and the second one is having the threads per block. So here, threads per block, and here the number of blocks. We need to make sure that the number of blocks is enough. So here is like a formula that you can use always. The size of your array plus the threads per block minus 1 over threads per block. This ensures that you have will ensure that you have like enough blocks. We are just see what is the size of our array. We make it like we increase it by one more block for safety, and we minus it by one, and then we divide it by the thread block. So like this number will be integer at the end, and it will have like we'll have like the sufficient number of blocks. So then lastly, we need to calculate the time spent for this kind of situation. So we'll just calculate the time for the GPU, spent on the GPU before, and we'll just put here the, if there is a problem, we can ignore it. And don't forget the CUDA device synchronize, so it doesn't continue to do anything on the CPU before it finish. And last thing is time, and we calculate the time. Just this is for timing only. And after which we finish like our kernel, we are just copy back the result from the GPU to the CPU. So the difference here, as you can see, like that here, the host to the device, here from the device to the host. And as you can see here is CUDA memory copy host to device, here CUDA mem copy device to host. So before we finish, let's just okay, this is the execution time. Okay, so this part is, let me make sure of something. Okay. Here just to like take the first element and make sure that the HCPU and HGPU like they have the same results. And last thing is to print the execution time for the CPU and for the GPU. Before we finish, you should clean all the device memories that you opened. So for example, CUDA free device A, you should free the memory. And also for the others, this is for the GPU, and for the CPU, we will do the same, but for the CPU, we'll do delete. It's called delete. And then after we finish, we should return 0. Okay, so here, let's CPU this GPU, this GPU. Okay, and then we just execute CPU. this GPU. As you can remember, this is a 100 million size array. So as you can see, like here, we have like a kernel execution failure. It's, yeah, here, conch porting CPU. Okay. So probably we forgot something. However, I have like the original code that I wrote before. Let's just try again. Here, BCC. Yes. Yeah, as you can see here, as we can see, like we are printing the first element, for example, the second element, and the summation, and the for loop can get us like the same value as the GPU can give us the same value as the CPU, which means that we are doing everything correctly. And as you can see, the CPU execution time is 224 milliseconds, which is about a quarter of a second. And for the GPU execution, it's 5 milliseconds only. So like we can see like how the GPU can outperform the CPU. However, I would like to say that it's not an accurate because the copy from the CPU to the GPU and from the GPU to the CPU take a lot of time, take more time than that, and we should like take this into consideration while we compare. But at the end, if you are doing multiple operations, then doing it on the GPU will like be more performant than doing it on the CPU. And as you can see, like the execution time for the process itself, it's decreased a lot, like from 224 to 5 milliseconds. So I finished. Sorry that I couldn't finish late. It was so important. I tried to be like as fast as I can, so we can have like some time for questions. And thank you for your listening.
Thank you very much, Mohamed Ahmed.
Thank you, Professor.
You've done your job very well, going through all the elements about parallel programming. You've done part one. This was, of course, part two. It is, ladies and gentlemen, now your job to just follow up and ask questions about anything that you do not quite understand. I do realize that we are very nearly about to run out of time, but we will manage to accommodate one or two questions. The first one coming from CC Jules Haber. We are listening to you, CC.
Okay, thank you very much.
Thank
I
you.
just have I just have three questions about
Please
this.
let's try to address one question at a time.
Okay. It's the same questions. It's just they are similar. Okay. What I can see from this code, first I congratulate Mr. Mohamed because this is a really computer technology based work regarding the code instruction from programming. So I just want to say first, when he explained before the data transmission from the host to the device, from the CPU to the GPU, and in the GPU there is a compute activity, and from the GPU now the data sent back to the CPU.
Yes, correct.
Okay, this is, I think this coding from the C+ is reflecting the schema is explained before. I just want to know, somewhere he put the index. He did a calculation from the index, like the index equal to block index times block index itself, plus trade index. Okay.
Yes, correct.
I just want to know why he made the how they call it, the times itself for the trade in the index. I want to know, and plus again the trade. I want to say why you did the block times the block itself, index from the block times the block itself, plus now the trade index to calculate, to initialize, or to set the integer index.
Okay,
Just want to know this.
that's a really great question. So
Yes.
thank you for this question. So what we are doing here is that like as I said before, like we have like a multiple blocks, and each block have a number of threads in it. We need to make ensure that each thread that is being called have a unique index. So how we do this? We do this by like we have each block have like it's indexed from 0 to the number of blocks we have, and each thread inside each block have an index from 0 to the number of thread per block. So the block dimension x represent the number of threads in each block, whether it's 512 or 1214, whatever. Here we choose it to be, it's the same as the block size. So like here we choose it as 520, 12. So the block dimension.x is 512 multiplied by the block index. So like the block index, example that, imagine that we have 10 blocks. This means that we have these blocks indexed from 0 to 9. So this means that each block is indexed from 0 to 9. So like, for example, imagine that the second block, this means that we multiply the second block by the block dimension index, which means that I have like the block that is index number 2. It means that before it is 1 and 0. So before it is 2 blocks. So 512 times 2 is 1024. So this block means that it have before it 1024 block plus the thread inside this block. So each thread inside this block will be added to this 1024. So imagine that the 256 thread inside the second block. This means that 256 plus 1024, so it gives this thread or this core a unique index. It can be replicated, and we can then each index can give us like a value from 0 to the number of the size of the array. Could you understand like this?
Thank you very much, Mohamed. Let's go to the second question, this time coming from Dr. Jane Toshukud. We're listening to you, Dr. Jane.
Good evening, Prof.
Good evening.
Good evening.
Quite a good presentation from Dr. Ahmed.
Thank you.
Having taught us about the parallel programming, the CPU, which is the multiple, and the GPU, which is the thousands. I think I've experienced using both the CPU and the GPU, which goes on our machine selection, IVED, BVAS, and all that. And the GPU, who goes on the mobile phones we use, the computer, and all that. Now, having this, if you want to use cybersecurity on both, whether it is CPU or GPU, because I know in the usage of the GPU in cybersecurity, it goes with like installing antivirus. It goes like a year, 360 days. My question is, in usage of the both, do you still use multiple for CPU cybersecurity and thousands for GPU cybersecurity? Thank you.
Thank you, Dr. Jane, for your question. If I understand correctly, so you are saying how we can use the GPU in cybersecurity.
Yes.
For me, like I'm not specialized in cybersecurity. Like my answer to this like would be like a general idea. What I know is that in cybersecurity, it's very important the encryption and how we are doing the encryption, and if you are generating password, how many combination can you generate in at this time. So for me, like if I'm cybersecurity and I will use this, so like the GPU can give you like maybe a more flexibility to generate like a huge number of combination of encryption at the same time in a less amount of time. So this can be like the benefit in your field, but I don't know like how it's used specifically and to what extent.
Thank you very much for your clarification, Mohamed.
Thank you.
As I said again, and very unfortunately, we sort of already run out of time, ladies and gentlemen. But let me quickly address or ask Mohamed to address this question, which would most likely benefit everybody. That is from Emmanuel Owoure, and this is what Emmanuel asked Mohamed. Are there compatibility issues between CPU and GPU?
Uh, Compatibility issues for like I believe no. I didn't face any compatibility issue between the CPU and the GPU so far. The compiler from NVIDIA is handling what is being done between the CPU and the GPU, and they are separate devices. So like you can still execute some stuff on the CPU until the GPU is finishing. It's just like a matter of code, how you write your code and how you can handle this. But the compatibility issues, no.
Okay, very good, very clear. Thank you very much. You've done a really superb job, Mohamed. We all understand that when it comes to issues like this, there are so many technical terms that we might have to struggle with, which makes a global, general understanding of basic programming necessary to truly grasp, assimilate, understand these issues in parallel programming. But no matter what, the job performed by Mohamed Ahmed today was really outstanding from all vantage points. And I very, very highly commend you for this performance, Mohamed. That is on behalf of the entire Atlantic International University. I'm
Thank
also
you, Professor.
speaking on behalf of each and every participant. I have observed them pretty well, very closely up front, so to speak, and I do understand they were all happy with the job that you have performed. Thank you very much, Mohamed, and we
Thank you,
hope
Professor.
to have you very, very soon again. And at this time, we all together are joining our voices to say thank you. Your mics are on, ladies and gentlemen.
Thank you.
Thank you, Muhammad.
Thank you,
God
thank
bless
you,
you.
thank you
You
very much.
really wonderful.
Bye bye.
Thank you.
Bye bye.
Bye.
Thank you very much.
Bye.
Hope to
We
get
also
again
remind
each
you
other
real quick.
next time.
We
Thank you
also
very
remind you
much.
real quick
Bye.
that the entire
Bye. Bye.
is also on your
Thank you. Bye
records. Thank you
bye.
very much.
Thank
Bye-bye.
you. Thank you, Professor. Thank you all. Have a
Thank
good
you.
day.